Um, okay. Good evening to all, and thank you for being here so late at night. And I also like to say thank you to PA to give me this opportunity to give you all of you, mostly some tips for you not to spend so much time doing static models. Okay. So my presentation today will be reservoir model characterization and design. So let me start. So a little thing about me. So I have 25 years experience in oil and gas industry. I'm a senior reservoir geologist, but nowadays I'm a consultant for oil and energy. My relevant work experience include reservoir geology, reservoir characterization, some seismic interpretation, and also I spend my my life, more or less my life, studying and doing some and applying some techniques like neural networks for rock types, okay, and artificial neural networks. It's better saying like this. My strong skills basically is integration of all the disciplines, like because 25 years allow me to learn a little more about the other disciplines, so I can more or less work with these disciplines and do the same. So I did several publications and presentations in institutions around the world. The last one was in ADIPEC. It was my third time in ADIPEC, and because of the pandemic, I had to do it by creating a video, and I was at home, and it was not really what I felt in last year in ADIPEC. So it's different. Uh, Today agenda. So today I will try to explain and ask you these questions. Why we need to make a model and what will be the purpose of that model. In this item, I will also show you not a common software workflow, but a typical workflow that we need to follow. At least in our mind, we need to have that workflow inside, okay? I remove from this agenda one part of concepts because they are so big, explanations are long, and in 1 hour it will be difficult. So I decided to remove model concepts, okay? Because I was trying to create one issue that it's called stratigraphic sequence for carbonates, and it's very long, and I decided, okay, next webinar probably can do it. But I didn't remove this part, deterministic models versus probabilistic models, and some essential geostatistics. These are very important. Most of the time, we don't pay attention so much at this part as a reservoir geologist, for example, or a geomodeler, but they are very, very important. I will show you why. Then I will try to explain reservoir model types. There are several ones, depends on your purpose. Then again, property models. You know already this for sure. So you have faces and or rock type model. You can have porosity model, permeability model, and saturation model. But again, I'm not going to explain how to do it. This is another issue, okay? And finally, because this is the workflow basically that a geomodeler follow, because at the end you need to show some results to your managers. So you need to have types. So I'm going to show you this, how to calculate, and the uncertainty that you have in all your model, for sure. Okay, so let's start by asking this question. Why we need to do a reservoir model characterization? This is the answer. So we do reservoir characterization because we want to integrate everything inside our model. So we need to combine different interpretative data sets inside of our database. But before doing that, it's important to understand the data. You, luckily, will have lots of different types of data. You can have logs, seismic data, you can have maps. Sometimes analogs are also important to include in your model. So you have a big lack of data. And again, you need to have a multidisciplinary teams. So why? You cannot work in all of these completely alone. We don't do alone models, okay? You need an interdisciplinary team together. Uh, you also need to have a common terminology between all of you. You need to understand, for example, scales. And scales are an issue very important in your model. You cannot combine a large scale with a small scale without doing something. And I will show what things you need to do. You also face limitation of the data. Search for critical elements, and a most important thing, special for your manager, and for the viability of your project is the cost and time efficiency in interpretation. After you see all of this, you need to evaluate your data project. So, and you have to think, all of the data that I imported in my project are adequate? Do we need more data? Do we need to pay attention to the sources? What will be or what is the best scale for my data? Do the data represent large area? Can it be extrapolated to other areas, or do we have data with some limitations? And let me grab this last sentence, data limitations. And this is, you will see that I put in blue and with the question, with the exclamation. It's always advice, okay? Consider this as advice. So if you are planning acquisition, you will often ignore something. So you need really to do a very good job planning. Why you are doing that? If you don't do it, you will see red points, and the red points are here. You will see impact of each parameter cannot be predicted. The important data sometimes cannot be collected. Your model is limited by wells with least information. Waste your time, especially waste your time. At the end of the day, you spend 8 hours or more with your model, and you feel that okay, my data is not good enough. So why I acquire this kind of data? Repetitions, you also can have repetitions. Costs, you can have increase. You cannot imagine the increase of value in if you acquire wrong data and the wrong scales and so on. This is a long story. And then I put in green here what you have to do. So you have to start by data planning always. And you can ask your questions like why I need that, what will be the number of users for that data, type and quantity, what will be the costs, when we require this data, who is a responsible party. Sometimes you don't acquire your data, you are asking different companies to collect your data. And I'm thinking, for example, core. You have core data. You don't do it in your company. You are not going there to collect cores. You ask some other companies to collect data. So you need to be aware of this. Data collection. So you are in your concession or in your field and you need exactly know where to collect your data. So you have to prepare yourself to ask that companies, but you have to indicate, you have to show where to collect the data. and how often. And I'm thinking, for example, in pressures. How often do I have to go to that gauge to collect that pressure? Also to correct procedures. Sometimes we need to again adjust. Imagine that you don't have the good data, so you need to adjust your plan and see if you with this adjusting you can collect better data. Also, sometimes it's important to have audits, people that are coming outside to our company to see if we are doing a great job. And for sure, we need data maintenance, okay? Database maintenance. You cannot import everything. You need to be aware of this, okay? Then the next step is data analysis and reduction. So we need to be sure that and trust that that data that we are import is the correct data. And you need to also to have confidence in that data. And finally, the final step is data synthesis. So integration of all data and synthesis of the data. Okay. And again, a kind of advice. So if you are doing reservoir characterization, you are collecting data. With that data, what you have is information. And with information comes the knowledge. So this is what reservoir characterization means: data, information, and knowledge. Okay. Okay. One more question. Should we want to build a full field model and use the results for answering a business question? Normally, it's a tricky question, okay? It's very tricky question because as a geologist, for example, we need all of data. We don't care about the costs. We just want this and that, and and we don't pay attention to the amount of money that the company will spend. So you need to be more conscientious what you ask with what you ask, okay? But there are several rules that we need to follow when we are starting a model. So the model must be coherent. Coherent with what? With your structural framework, with your geology, with your dynamic data, and special follow your objectives when you start a model. The model that you are doing must capture the heterogeneity of the field, okay? And you have a model that fits to the purpose. And the grid size. The grid size, again, you define your skeleton, and the grid size are very important to be correct, and that this grid must be linked to the required degree of detail. Okay? The complexity of the model, again, it's an important issue and must be linked to the amount of data and the degree of heterogeneity of the reservoir. The model should be accurate. Be aware that the upscale not always follow the details in the geostatic model. So the upscaling is one important task that you need to pay attention, and special, you need to do it with your reservoir engineering close to you, okay? As a modeler, you need to be kind of participate. It's a team. You need to have inside of your team these guys as a reservoir engineering when you are doing the upscale, because they could check if your upscale is correct and and come back again to you. So it's a cycle. So you can check and you can give results to your reservoir engineering more correctly. And again, you have to ensure that the model reproduces the dynamic results, okay? Now, model purpose. You can do any type of model. depends on your purpose. So, and this will affect, of course, the results. Okay. So you have different types of purpose. So I choose here the model for comfort. This is a fulfilled, this is just a sketch. It's a fulfilled model. And imagine that your manager wants to have 3 wells in a specific area. And we decided to be this channel, yellow channel. And he asks you to give the location of these wells. So you can prepare this model for comfort by dividing in, for example, in 3 different models. And each model has a certain difference. And with that difference, you can generate this information for your manager. And we call this model for comfort. So usually you use this model, as I mentioned before, for decision making, and these models allow you to decide what will be the best, in this case, property, or best percentage of sand, whatever. Okay. We apply these models in mature fields when the presence of inherent model already anchors. And for conscious choice, imagine that your manager see this full model and he see 3 wells and he ask you why you put here, why not putting there. So you have already prepared your answer, okay? And for a conscientious choice, to move away from the default of a single detail fulfilled model. It's another use for this type of model, and it's very easy to update. Okay. Model visualization alone. This is, if you look at the picture, it's very strange and it combines different informations. You have here, for example, Google Maps, some contours, and you have this cross section, okay? But model for visualization alone is used for more cross disciplines. You can have geophysics participating in this model, petrophysics, reservoir engineering, well engineering, and accept teams, okay? But they are able to visualize the reservoir in 3D. Must be your issue, because it's more easy to see in 3D, okay? It's a great understanding for sharing, and reduce uncertainty of a subsurface, the risks, and promote useful discussion beyond the team. When your team see this, they can, for example, decide that, okay, this is not the good position because of the this cross section is not giving idea. Let's take another cross section. So it's more easy, and you see these gray stuffs are kind of cross sections that you can take along your model, and you can reach a point that you can have a better picture, and that better picture can allow you to show you to your managers for have a better decision. Okay, you don't need to show everything. Model for volumes. Okay, most of the times, what everyone in the company needs is money, no? And you make these models for getting some values of volumes. So this type of models, you have, if, in this case, is you want to know how much oil and gas you have here, and this is one of the first goals for these models. Can be done by using, of course, you can do it by using a map-based approach or a 3D software package. Nowadays, it's very difficult to use maps. We don't use maps so frequently. But if you go to the field and someone asks you to give a prediction for that well that you are drilling in your field, you can do it by hand in using a map, okay? This is it can be quick and easy for a given uncertainty, and their impact in volumetrics can be coarse and a fast model, but you can also have you also don't need here the permeabilities, and permeabilities, you know that they are a big issue when we are doing permeability models. And if we give the permeability models from static to dynamic, they will ask you a lot of questions. So permeability is one of the red lights in static models, okay? And cell blocks for this calculation in volumes can be large, okay? I have to drink water. Next, models, you can have models as a front end to simulation. Most of the reservoir engineerings already know these kind of maps or models, but they are special for simulators. The heterogeneity, you need to capture the heterogeneity, and the property that needs more to be aware is the permeability. The reservoir performance can be very important, and you must use a fine scale model because permeability is a non-additive property. And you know that permeability plays an important role in simulation. So you really need to pay attention to the permeability, and you need to see if this permeability is very well controlled. And that's why you have to be close to the geologist or static or the modeler before going further in your dynamic model. Okay. You also have models for well planning. See this one? They are designed for well planning and geosteering. No special requirements. You only need a structure, map, and some wells. And you can also have seismic attribute. They are fairly costly models, and most of the geoscience softwares like Petrel, Jest softwares have this package already available, and you can plan a well. The planning must be done in models designed to be largely deterministic. Later on, I will give ideas about comparison between deterministic and non-deterministic. Okay. Now, I put this model for storage because nowadays we are trying to use the models, static models and dynamic models, for storage CO2. Okay, this is one example. You can have in this type of model, you can have storage, and in this case, injection. Okay, and the big change in storing CO2 is controlling gas emissions. Again, we need models to understand the injection of CO2 in more detail. Needs good permeability. In this case, these models has to be with a good permeability zones, and some important flow barriers can be faults, okay? And pressure compartments. Needs also a good understanding of the formation to elevate pressures and geochemical reactions due to CO2 dissolved in brine. But what I want to highlight is the storage CO2 normally requires a large aquifer or a reservoir volumes and some cap rock systems. So the challenges for grading resolution and detail must come as a primary thing. Okay, you need to think, if you, in this case, if you decided to have a CO2 storage, you need to create a model that pay attention to the grid resolution. Okay. But as I said, there is another models. For example, fit to purpose model, most common one. Models for EOR, and models for seismic modeling and more. Okay. Now I'm going to show you the basic workflow in order to finish this chapter 1. Let me see if I can zoom this. Yeah. So these are coming from this guy, Philip Ringelgross, and he creates this workflow that I think they are very important, and a general workflow, not a software workflow. Okay. So first you have your data. You plan, you decided what you want to acquire, ask for money from your managers, everything. Then you decided with that data what will be your model purpose. Imagine that you want, for example, to draw or to plan for new wells. So it's more easy, okay? It's explained like this. So, and also you need to establish in your mind what will be the conceptual geological model. Sometimes we draw a picture, and that picture can be inside the software as a soft data, and you use that for constrain your data. Okay. You can build rock models. You can build property models like net to gross, porosity, saturation, permeability. Okay, rock types, species. I'm just giving models. Assign, and that's your static part more or less. Then you assign flow properties and functions. And this part you need your reservoir engineering to give that information. Then you do the upscale flow properties and functions. When you do the upscale, please be with reservoir engineering. This is my biggest advice. Don't do it yourself because alone, at least alone, because you will need to talk with your reservoir engineering because he has ideas already in his mind, and with yours it will create a great upscale that you can do it one or twice and you don't spend weeks doing that. Okay. Make forecasts. You can predict your production for future and assess and handle uncertainty. When you have all of these, you can go to economics and take a decision. But if your economics doesn't allow you to go further, please come back, do it again, keep the same surface database where you already spent a lot of money and time. Preserve this model, the first model or the second, this model that you did, because you have to have a decision track. Discard or achieve models results and address the next question. Okay, so this doesn't work. So what can I do and change? This slide you are going to see it more or less at the end of the presentation, but this is just to highlight important things. For example, you need to integrate different types of data. Before your model, you need to have collect all the information in digital or in papers, but nowadays it's digital. Have a very strong quality control. Don't don't cross this step because you see, for example, when you are importing wells, you have an ASCII file and your well are I don't know 100 wells, and for well, okay, 20 wells, you just check the file inside because ASCII file you can open in Notepad as a text file, and you can see inside what is the values, what is the type of logs. But please do all. It's very important. I know it's I'm saying like oh come on, it's so much, so many wells, but please do it because at the end you will see that is one of the tools most important, the quality control. Imagine that you at the final of your model you pass to your reservoir engineering to do the dynamic and you find a mistake. Can you imagine the time and the money that you spent? So do a quality control. Then you have to think and decide which approach better suits for your project. Another task that it's very important when you are starting a static model is the coordinate reference system, the CRRS. You have to choose, you have to read your data. Now, normally, the people that are acquiring the data have already some coordinate reference system. You can use that coordinate reference system and create your model with that coordinate reference system. I'm just giving this to guarantee that you have the same thing from the people that are acquiring the data for you that you are doing reservoir static model, and for the dynamic have the same. So all of you at the end has a result, and the result is the same, and with the same coordinate reference system. Okay. Again, the units you cannot change the units in the middle of your model. You need to think first about the units and then start a geological model. Okay. The other advice that I'm going to give is to keep a record and documents of everything, because sometimes you have a map, you show your map to in one meeting to your manager, and the manager said, "Oh, no, 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 I don't like this because something happened and doesn't matter," and you come back to your office and you change. But at the end, you need to have results um, that are fine with you and fine with your manager. And imagine that your manager said, "No, no, I remember that you show me that first map and I want that first map in your model," for example. So you have to keep the records of everything. Please don't forget this rule. And for your reports, for sure, you have to save image to create folders and put your image there. And the best model is the one that built with a clear objective in mind. That's why before you start a model, think first what is the main objective of that model. If it is for drawing, planning new wells, if it is for comfort, you have to think what is the main objective of your model. So there is no accurate workflow for projects. All of them must be decided up front before any modeling effort started. I already mentioned this. So think first, plan everything, get your data, and then start a model. Okay. Let's now compare deterministics and probabilistics model. Here is two pictures. One is corresponding to the deterministic and the other is the probabilistic model. They look not similar, the colors are different, but they have different methods of working. So the deterministic models, the parameter values and the condition is initial must be determined. This model, I said this model is deterministic, must be with no random components. Each component and input is determined exactly. And I'm going to show how. This is just a chart. And if you imagine time versus prediction, let's see. You have a time, imagine here, this time, and you only have one prediction, okay? You don't have several, you just have one. And if you think that you are using a deterministic model. And deterministic models are important in object model or in the pixel model, or also in training image, okay? Now let's see what is a probabilistic model. So it's called stochastic model. So you have random forcing, random number forcing. You use for simulate deterministic systems that include small-scale phenomena that cannot be accurate, observed, or modeled. If you look here and imagine that we have a prediction, you can have different times. See this one? You can have this time here and this time over there. So this type of models can have it depends on the random number you are using. So it's not like you have only one model like this one, but you have different models. We call these um, runs. Okay. Now let's talk about geostatistic. I'm going to give you just some uh, few statistics. Geostatistic is a discipline, a very hard discipline to understand, but I will try to explain this in a way that if you have these concepts on in your mind, you don't need to have more to do a great model. Okay, so geostatistic is used to populate interval volumes. Okay, reduce a large amount of data into something more manageable and summarize numbers. So, as one of the concepts is the histograms. It's a graph used to represent frequency distribution of a few data points. It's composed by two perpendicular lines. One is in ordinate is the frequency, and in the abscissa is the quantity. The data can be or the data is organized in bins, and for sure the probability of a value R in the bin is high. Here is the histograms. Let me just try to zoom this. Okay. This is a common histogram. Imagine that X could be, I don't know, porosity, and you have here the frequency. What you can see here is this value of porosity has great frequency of being in all your model. Okay, this is important, and you need to put this in your report or in your presentation to give a better ideas to the others that are seeing your presentation. Give you more for you. It's more strong when you present this. If you just say numbers, okay? It's people usually likes to see graphs, maps, and pictures, okay? In below this picture over here is the real results from a model that I did once. And what I want to show you with this is the productive zone, and this is not productive zone. In productive zone, and this is for porosity, the blue is the model, okay, and the red is the well logs, and the green is the upscale logs. If you look here, you are getting higher, you are giving more importance of your to your model, because your model here, you have less, how can I say, not so high values, because your update are saying the opposite. Okay, so your upscale cells have higher values than your really model. So, and you see this mostly in these parts, in the parts that you don't have so high porosities, but here you have also the same. See this point over here. So the upscale is less than your model, your log is less than your model. So something wrong is here. Okay. And you need to pay attention to this. And that's why to have histograms, you do your model, of course, and you need to understand your histograms. You put your model, the histograms, and you do a quality control. This is one of the parts of the quality control, checking each point what happened. And you see that, okay, maybe this is not the greatest model for the porosity. Do I and think, okay, I need to do again, change some parameters, change some variograms. Probably it's because the variogram you need to think. That's what I meant with this, okay? Now, let's talk about cumulative distribution function. So, some cumulative distributions function is a summation of your values in bins as a value increase. So you plot your values versus total number of the values, and you get this type of chart. With this type of chart, you can see easily the P9 and P10. See here, this is P10, sorry, and this is P9. This type of chart it's great for using in sequential simulation, okay? But you also need to understand basic statistics like mean, median, mode, minimum, maximum, percentiles. You can generate this type of chart. And again, you can see P10, P50, and P9. This will be important, for example, in your STOIP. You can present this in your STOIP also. Okay. The variance. The variance is an important concept, and this concept gives you an idea about the width of the distribution. I don't know when. Okay. So the variance definition is a measure of the average difference between individual values and the mean of the data set they come from. So, and it's calculated with this formula. So you can see each value and is a result of the difference, average difference between individual values and the means divided by number of values. So this gives you an idea about the widest distribution. And you have here a map. So what you can see here is you have high values and low values. So you can see that this is great to put a well here and a well here so they can produce something. And this type of map normally is similar to a kriging. Kriging is an algorithm that gives you a maps and also a model. But this is just a map. And you can see that you can plant with this a well. You don't need more, go further if you don't have I don't know, if you don't have that objective to go further, or if you don't have enough money, whatever, you can do this. Another concept that is important in inside your model is correlation coefficients. Okay, this is a strength, the measure the strength of dependency between two parameters by comparing how far pairs of values deviate from the straight line function. This is the definition. You don't need to memorize definitions. You have the formula, and the formula looks like confusion and difficult, but it's not. You just have to take from your mean values the initial points, and you can reach these. You can create a table, but the software, and I'm talking now about Petrel and Jazz also, the software gives you immediately these calculations, so you don't need to these formulas, but it's just for you to understand, okay? The outcome can be 1, 0, positive or negative. It's positive if the higher values of X tends to occur with higher values of Y. So you say it's a positive correlation. If it is 1, the relation between X and Y is a simple straight line, like this. You have this and you have a straight line. If it is zero, no correlation at all. So it's like this property compare with the other, it's not possible to compare, okay? Negative, higher values, it's the other opposite of this. So higher values project with lower values can give you a negative correlation. Here is the scheme. This situation, if you have, for example, porosity against permeability, and you see this, you say, in this field, there is no correlation with porosity and permeability. So you have the correlate coefficient as 0. In this situation means that you have a perfect correlation between porosity and permeability, more or less 99. It's a very good correlation. It's not common, it's at all, okay? Sometimes if we see this, we say, oh, come on, I did something wrong. It's more like 0.07, 0.75, 0.8, but 99, no. And here is the negative correlation. Still, you can say that porosity and permeability has a correlation, but it's negative, okay? Advice. The correlation between porosity and permeability is typically in reservoir modeling, but the values varies comes from 0 to 1 or 0 to 100%. If you have 0.7, you can consider that it's a very good correlation in porosity with porosity and permeability. Variograms. Variograms are famous and very complex and belongs to one of the models of the softwares, like data analysis. So that's why you need, and the variograms depends on your sensibility and the knowledge that you have already of your field. I have to drink water again. Okay. So variogram correctly is a semi-variogram, and it's a function that describes increased variation in phenom with increased distance. It's expressed as an average square between pair of data in the data sets. Has this formula. So this is a semi-variogram over here. And the function can be calculated for all the pairs, and in that way can use an example in the irregularly scattered wells. Here is a variogram. You see this picture for sure in a lot of softwares. In this case, this is one coming from Petrel software. And what you have here is the property, the experimental variogram data points, the property that you have. You have here the variogram axis and the distant axis. Let me put here. So you have the nugget. Then the nugget is extrapolate variogram when the variograms are 0. The still, this part over here, is the constant where the variogram may be approached for wide upspace pairs and approximates the variance, and the range right here, is the distance at which the still is reached. This is like, well, you need to know that you have a still, you have to know an edge, and you have to have a range. But you can have different approach. This is one of the approach. Depends on you and depends what you already know of this field. Imagine that you can draw this variogram going the highest part over here. So you are giving more importance to this property than when you are using this one. And sometimes when you imagine you reach the final results type, and your manager said, "Oh, it's so small. You cannot. It's not good enough to develop this project." And you can ask, "Okay, maybe I can change something here that it depends on me. So let me ask the statistical guy or a consultant, for example. You can ask to external person, and maybe that person see that, okay, you did an approach to your variogram that it's not properly. Let's try to give more importance to this part over here, reduce this part over there." So you can adjust your variogram and you can see this adjustment in your model. This is one of the things, okay? I said already, but there is different models. So you have here a lot. Basically, what we use more is the exponential and the spherical. I cannot distinguish colors. I hope you can. But for example, in exponential, the greens is used for, we apply that variograms, at least myself, for different projects, and it works very, very good. So how do you face statistics? So the idea is to have a good communication between teams, to have trained experts, special to someone that already understands correctly the statistics and can help you, since you are just in the middle of the disciplines, you are a modeler or something. And you need a strong project leader, because you are going to ask, imagine you are going to ask to your project leader, please give me money to external, to pay to an external consult. So you have to have this kind of um, if you don't have a strong project leader, probably said no, you, I cannot spend too much money here, continue your project and leave it like that. So it's not good enough, your this answer. You are to realize data digital, adequate computer resource. So if you do a full field development plan, for sure you need a very powerful computer with a very capacity and lots of space in disk or in servers. So you need to think what type of project or model you are going to do. You need to have management support. As I said, you need to have a manager that can say, okay, I can give you more to your model if you at the end give me a better result. See, kind of giving and taking something. And you need to have a technical support staff. Let me show you here an example of a variogram. Okay, imagine this is porosity, and you have here the variance and the leg distance in axis. And you see that you have already attended this. So if I draw a line like this, it's a possibility. Or if I can give more values for this property, like porosity, I can probably go like this, and you are adjusting a theoretical model here. See, and this is just a supposition, but you can have different one. I decided to have this one because it could fix most of my points. And you know that the first part that you have to give importance is this one, because it's your range, the biggest range. Here is the still, it's where you, from here to here, it doesn't affect your model anymore, because this part is the most important. The nudget is where you already said, where you have the variogram as 0, you have a range, and you have a still. What I want to mention here is the semi-variograms, these ones, can be derived from a different data sets, but the data set is only a sample, more or less imperfect. It is belief model. You never have a perfect model, never, okay? You just have a useful model, okay? Don't forget this. So what is the reservoir model? So reservoir model is a representation of a physical and chemical properties for an oil and gas reservoir based on data various sources. So capture knowledge of their subsurface, can give a first idea about the stock volumes and help your management decision, development plans and well targets, and so on. So it needs a series of data to build a series of models. Again, an advice. So before starting any model, it's important a compilation and see your data. It's important to think in terms of static and dynamic data, because you are just a static person. So you are doing static models and you think only in your data, but you need to think also in dynamic data, because you need to see if that in dynamic data can help you to better define your static model. And I'm thinking, for example, in pressures. you know that pressures are important for dynamic people, and if you have a model that don't show them there is a zone with high pressures there, they don't care about the model and they say, oh, you did the wrong model, give me another, and you have again to spend your time and so on. The static model. So we deal with hard data. So these hard data are data that are coming from direct measurements or computations, and soft data refers to inferred information. Okay, let me zoom this. So this is the sources of data for geomodeling. You can have in your static model, for example, seismic data, and use that seismic data for what? For structural maps and faults, for controlling the quality, processing, static correlations. Let me just, I don't want to read this. So cores and descriptions. Why you use cores and descriptions? Use core and descriptions for facies, the positional environment analysis, core analysis. You see pore and perm charts, and you can define also here the rock types, and this is another issue that is important. You can see the mineralogy, some hydrocarbons shows, for example, mud loggings for rock description and mineralogy, and so on. But you also have soft data, and soft data are coming from geological model. And there you have the positional environments, tectonic story, genetic evolution. These things are very important to have a good static model, okay? Especially if you are working in carbonates. Seismic attributes, also important. And you have a series of seismic attributes that can give you immediately the shape of your geobodies, and that's also important to calculate, for example, the stopping in that geobodies. Okay, and the proper calibration to the geology. Oops, so sorry. Okay. Types of models, and now another issue. You have conceptual models, numerical models, deterministic models, and artificial neural network models. This one, I think I'm going to spend time here. In artificial neural network models, you can use these to generate rock types. It's important because you can link your facies to your rock types, then to the porosity, then to the permeability, then to the saturation. And at the end, you are certain that for each point you choose, they are very well linked. And you can say, like, for example, I have this porosity that has a good permeability, this value over here, and this value over here corresponds this saturation because my rock type was the best, for example. And that's why you need to link your models. This is your typical workflow. So in Petrel, for example, and I put here, you already know this picture, so I'm not going to spend too much time here, but this workflow can be adjusted to your project. It's not like you have to follow this exactly. You can adjust. Probably you can include more things here and make more models, okay? For example, here you don't see rock type models, and you can include rock type models. Let me talk, now it's the rock type, it's reservoir models, and I'm not going to explain how to do a model, a static model, but I decided to just grab a part of that workflow, structural modeling, and talk about this. So these structural models usually are coming from seismic interpretation, but they can be based on geological surface, and they have to be tied to the well markers or with the structural maps, okay? You can have a structural map coming from the seismic, but then you need to do a step that is linked to your well markers, okay? And your well markers, you know, that are coming from for example, from your logs, okay? But sometimes they can be because someone saw it and you are going to use his interpretation. And you can say, okay, his interpretation can give me already a good point and I can correlate with my other wells. Or you see in Bible, in books, okay? It depends on this. Also, you need to incorporate information like faults, like layers, like horizons or boundaries. You limit your model by a boundary. You cannot. You need a boundary for all of your model, not only for this one. You also use seismic and well dated for the geometry and the orientation. And of the reservoir feature and apply geostatistical methods to interpolate and extrapolate data between the wells. So you know exactly, or at least you think you know exactly what happened in your wells, but for the rest part, you have to use geostatistic like variograms, like histograms. See, you need to use statistics. You also need to incorporate the positional environment, diagenesis and tectonic history. Okay. Here I'm going to again highlight the importance of a good data set. So you are here thinking where there are any special or trends in my data. Do I have analogs to use as a background? How many folds do I have? How will the grid be oriented? Can be oriented by a fault, can be oriented by something, by a trend. So you need to have these ideas and more ideas. What will be my area of interest? I have a big project, but somehow I need to cut my area because for after my wells in the parts that I don't have wells, I cannot create a model because a model will be just a statistical model, not probably not a real one. So I need to define the area of interest. What will be my geological environment? And you know that you can have different types of environments. What will be my primary direction flow? And this part you have to talk with your reservoir engineering. What is the objective of the project? For example, what will be the use of this simulation, history match, well planning? What is my conceptual model? How many wells? See, let me go back. With this, you have to think. That's why I put this little toy toy thinking. And you need also to think this before you do anything, okay? And I have here some rules. My advice here is to just print these and put in front of you when you are doing a model because they are serious rules and you have to follow. So one of them, the first one is must be coherent with your structural framework, geology, dynamic data, and suite to address the key objectives of the model exercise. I already talked about this. So it's the question of to link everything and everything must be in exact position. That's why, again, you need a very good correlation, CRRS, Coordinate Reference System. Your model must capture key heterogeneities, must establish key objectives of modeling and design model to meet these. So it's a model to fit the purpose. The grid size must be linked to the required degree of detail and capture your problems. The complexity of the model must be linked to amount of data and degree of heterogeneity in the reservoir. The model cannot be precise representation of the reservoir, but should be accurate. That's why you have a different number of static models, but you cannot say this is the correct one. You have a degree of uncertainty, okay? Here you have a degree of uncertainty. The upscale always degrades the input data. So you can, when you just do the upscale, you are passing from the geological model, so a fine model, to a coarse model for the dynamic. And you, for sure, you need that because the dynamic needs to run simulations, and running simulations needs computer space. So maybe this is a good idea to do the upscale again with your geologist or geomodeler and reservoir engineering. And another thing that I have to highlight is the importance in your data set is your data integration. So data integration consists of your data compilation and the quality assessment and integration. These three things: compilation, quality assessment, and integration. The objective of doing that is to unify or link all together in one database, correct one. And then you have to do a quality control, analysis, mapping, and transformation. The other important issue in your data set is the scales. You have to combine different types of scales. For example, let me just again zoom this. These are charts that are coming from SP, both, see, SP. And it depends on your scale. And why I'm saying this, if you are using thin sections, you are expecting to have scales very, very small, see? But for example, if you are using logs, you are expecting to have logs with high scale. You can see exactly what is in your log. And this can be used in disciplines. Imagine in thin sections, you can have diagrams. You can extract the diagrams from these thin sections with other information, okay? And for logs, for example, you can have a good log interpretation. So you for sure know that marker over here is the starting of your unit A, or you see what I'm saying? So you must know what scale you are working, okay? And then you have the property models. These models you already know. So this is the porosity, permeability, probably saturation, and here is the phases. I'm not going to explain how you do this, but the only thing I want to highlight is you have to link these together. If you have a facies model or a rock type model, please link with your porosity and your permeability. I didn't have here the saturation, but it's okay. So you link all together in order to, for example, if you want exactly to know a point where you see good porosity, you have to think, okay, let's see what will be the permeability, what will be the saturation. And since it is linked, you have great results, okay? For example, in several techniques that you can use when you are doing model is the kriging, I already mentioned, the Gaussian simulation, variograms, and so on, okay? And here is the results. It's an example for sure. I don't know what example is this, but for example, here is your structural model, okay? You have to put here what? You have this structural model, sometimes the surface coming from the seismic interpretation, and you have here the zonation, you do the zonation, you put the layers, then here you have the porosity here. So you run the variograms, you prepare your data analysis, you have your log. Sometimes you have core information that you have to link to your log. So everything must be linked together because when you link, also let me just say this, when you link your core data and your log, be aware of this link thing, okay? Because sometimes you have a core and you have a log results, and they don't correspond each other. So, and you know exactly the depth position on where you take your core. So you need to first to see these, okay? And also you have here the permeability logs, and you can make a water saturation model and also a net to gross ratio. Some algorithms that you can use. Basically, Petrel use sequential Gauss simulation for porosity, and these give a realization that can be correlated with a random variable. Then you have a truncate Gauss simulation, and it's also great for getting the sand and clays, but you usually, oh, sorry. You don't apply this so much except to faces or rock type groups. Okay, you don't put this algorithm in when you are trying to get the porosity, for example, okay, or the permeability. Sequential Gauss simulation is used for the seismic impedance, for example, okay, and here you use discrete data as binary, and this is great for this type of situations. Finally, or not finally, I'm going to show you the formula. Why I'm showing the formula? Just to give you the the issues that you need to have before you're going to say to your manager, this is my STOIP, okay? So STOIP is a relation between properties like net pay thickness, porosity, water saturation. But you need also to know the area. But this constant over here depends on your units. You can have different constant here. So if you see different constants, don't choose this formula or the other formula if you don't see the units. I did that mistake once, so I got immediately the formula, and I was in a rush, so I just do the easy calculations for my manager. And when he saw the value, he said it's wrong. And I was, come on, and I was completely, come on, how it can be wrong? I used the formula, but I forgot to see what were the units of my net pay thickness and my volume over here. Okay, so I made a mistake, and I don't want you to make that mistake. The same for gas in place. So you have here the formula. And finally, I'm going to speak about uncertainty. Uncertainty, you can have uncertainty in all your model. Coming from the geophysical uncertainties, like when you do the interpretation, seismic interpretation, it depends on you. I can do an interpretation, you can do another one, and who is the correct one, who is the wrong one, far away from the wells, the control of the wells, you don't know. But if you know that you are playing with the certainty, that's correct, that's right, and you can continue. But you can have the uncertainty in modifying the migration, in time depth conversion, in peaking, in well ties. See, a lot of things that you in seismic you can have uncertainty. Also in geological, sedimentary, and petrophysical uncertainty. Where? Well, you are working with wells, you are working with geology, and geology you never know, and you are working with petrophysical also. So the petrophysic is a person, and the person has an ideas, and sometimes you as a geologist have different ideas. So again, who is going to be the lucky one to get the correct result? You don't know. So you have uncertainty here also. And in dynamic, where in dynamic? In absolute relative permeabilities and fault transmissivities, for example. So, and this can create a great impact on reserves and production. I decided to use this scheme over here, and I have to zoom, okay? So let's start. Where you have uncertainty in gross rock volume, for example, and where in the structure or in fluid contacts. And this is like playing dice. You just you don't know. You are just getting ideas from your data. So here is a great place to have uncertainty. Also, you have uncertainty in phases volume fraction. So you decided to use the faces here because your log said so, but probably is not here. So it will affect all of these properties because, as I said, you need to link all the properties. Okay, you make a mistake in one, you propagate your error for the rest of the properties. And also in reserves uncertainty, you still have here a big uncertainty in where the Corey exponents or in the fault seals or in the Kiefer size. You don't know where is the Kiefer size. Okay. Let me escape here. Finally, I'm almost at the end. Some brief notes and comments. Okay, before a model, you already hear this a lot from me. Once more, you are going to hear this. Before beginning a model, you need to collect all the information. And this information can come by digital or by papers, and you put everything in your computer, in your disk, whatever. Do a very strong quality control of the data. Think and decide which approach better suits your project. Choose a correct coordinate reference systems. Choose the correct units. Keep a record of all your documents, everything, and don't forget the date. You need to put some date, 12, 13, whatever, May or June, doesn't matter, but you need to record this correctly. And the date is one of the things that is give you an idea of how many attempts of that you do for getting the result. Frequently save image. Why you need to do that? Because as I think I mentioned before, you need to use in presentation and documentation. You need to write at the end a fulfilled report of your project. So you need to use that pictures. And the best model is the one that is built with a clear objective in mind and fits the purpose. Choose carefully your algorithms to be used and pay attention to the workstation capabilities. This is an uncertainty point. You can have, you start doing things, you start create your model, but if you don't see exactly the capability of your computer before you have this model, you are in troubles because at the end you cannot run nothing, and you sometimes needs to export the model, and sometimes there are keywords that you cannot export, and it's a mess. Believe me, you have to think first. Okay, and that's it. Okay, so keep calm. This is my advice. Sometimes you need to be calm. Keep calm and do a great model.